So recently in this course, we've been learning about data analysis. We've learned about descriptive statistics. We began to learn about inferential statistics, and in particular, we've been focusing on null hypothesis significance testing. We learned about correlation analysis, and now we're going to learn about the t-test. We've actually already seen an example of a t-test in R. You may recall we looked at an example where we were comparing different types of insecticides, and we decided to focus on spray C and spray D, and basically just comparing those two to test whether one is more effective at controlling insects than the other. So basically our null hypothesis would be that those two sprays are equally effective. Our alternative hypothesis is that the sprays are not equally effective, that one works better than the other. And we actually ran the t-test in R, and if I just pull up our other visual of that test result, I'm just going to pull up my laser pointer. So basically we went through the steps. I've already mentioned the hypotheses. Step 2 was to set the critical values. Critical values were 2.07 and negative 2.07. And then we found our test statistic t-obs in R, which was negative 3.08. And if we plot that here, we find that that is farther away from the null value of 0 than our critical value. So basically we have enough evidence to reject the null hypothesis and conclude that in this case spray C does actually work better than spray D at controlling insects, and we can see that reflected in their sample means as well. So the average from group C, or spray C I should say, was about 2 insects, and the average from spray D was about 5 insects. So we're going to look through a couple more examples in this video and in class as well. So the purpose of a t-test, again, it's a null hypothesis significance test. We're doing inferential statistics, and this test in particular is to examine whether there's a difference in the means of two populations. So we're going to use the symbol, the Greek letter mu, to refer to population means. So basically the null hypothesis is that those two means are equal for two different populations. Let's say, spray C, spray D, control group versus intervention group, whatever the case may be. The alternative hypothesis is that those population means are not equal. So again, the null would be that there's no difference. The alternative is that there is a difference. So by rejecting the null, that would imply that there's a statistically significant difference in those two groups, those two populations. So just to see a visual of that, here we have two different populations plotted in different colors. So let's say that the blue dots represent the control group, the red dots represent the intervention group. So basically whatever outcome that we're measuring, let's say it's some health outcome, so higher scores refer to better outcomes. So basically we can see that the intervention group is doing a little bit better than the control group. The question is, are they doing significantly better? So here's another visual with histograms instead, different colors, different symbols. So basically the symbols here are referring to the sample mean. So x bar, so mu we said was the population mean. X bar that you see here is the sample mean. So basically, again, is group 2 doing significantly better than group 1? In this case down here, you probably have a better case for there being statistical significance because the difference between those two means is greater. But again, we can use a t-test to actually test that. So there are a couple different types of t-tests, and in particular we're going to focus on the difference between independent t-tests and dependent t-tests. So independent samples are ones in which the scores from the two groups are in no way related to one another. So this is kind of typical of a true experiment where you have, for example, a placebo group and a drug group, or a control group and a treatment group. It would also maybe be relevant with doing gender comparisons if you have random groups of males and females that aren't related to each other in some way. A dependent samples design would be one in which the scores from the two groups are paired in some way. So for example, if you have males and females, but they're like spouses, like husbands and wives, and they're paired, then that would be dependent samples. If you have twins, if you have repeated measures on the same subjects, like you have each person participate in both the control condition and the experimental condition, or it's just like a pre and post design, so you're comparing each person's first score with their second score, or if you have, for example, if you treat the same person's left leg with one, say, lotion or something like that, and their right leg with another lotion, and you compare the outcomes between each person's left and right leg, then that, again, these are all examples of dependent designs. So it's basically the design of the study that will dictate whether it's an independent or dependent samples design. That's basically what it's saying here. So the design determines the type of t-test you'll use. So if subjects are randomly selected and assigned to separate groups, such as I said before, a control group and a treatment group, that would be an independent samples t-test. If the subjects are matched in some way, if they're paired, if there's a pre and post design, then that would be a dependent samples t-test. So let's see if you can identify the correct test. So you can pause the video, read each of the examples, and then decide which one is independent, which one's dependent. Okay, so you should conclude that in the first example with women's basketball and volleyball, that these are independent samples. Basically, we have two different teams, and we're comparing their vertical jump performance. If you look at the second example, you should notice that this is a dependent samples design. So basically, each person's first sprint is compared with their second sprint to see if those times have improved with training. So we're going to look at an example of an independent samples t-test. And so our research question here is, which results in better academic performance? Silent studying or studying with music? So let's say we set up an experiment where we randomly assign 10 subjects into two different groups of 5. So one group is going to silently study, the other group is going to study with music, and basically after studying for a period of time, again with either no music or music, they're going to take an exam and we're going to compare their scores to see if one of those studying strategies is more effective than the other. So the hypotheses are that for the null, that mu silent equals mu music. For the alternative, mu silent does not equal mu music. So basically, again, these are just the means of their test scores comparing between those two different conditions. Step 2 is to set the critical values. So with a sample of only 10 people, 5 per group, and deciding to use an alpha level of 0.05, which is pretty typical in research, at least in social sciences research, the critical values are negative 2.31 and positive 2.31. And then that brings us to step 3, which is to calculate the test statistic. Again, you'll typically use some type of computer software to calculate this for you. And remember that each test statistic is specific to the method that you're using. So with correlation, we said it was going to be R-obs. For a t-test, it's going to be T-obs. And basically, we can look at our sample data. So after silent studying, these were the exam scores of those 5 individuals. The mean of those scores is 86.4. After studying with music, those 5 individuals had these 5 scores, and the mean was 83.8. So basically, we can take the difference of those means by subtracting and find that the difference was 2.6 points different. And basically, you take that difference, you divide it by the standard error, which you don't need to know the details of this, but it's basically a combination of the standard deviations from those two groups. So the standard error in this case was 3.2. And when you divide, so you're basically calculating a ratio. So sometimes you hear this called the t ratio, the t statistic, the t value. They all mean the same thing. So we're calling it t obs because it's the observed t value. And this is 0.81. So when we compare t obs with t crit, we find that it is not farther away from 0. It's within the non-rejection region here, closer to 0 than the critical values. So we're not going to reject the null hypothesis. We're going to retain the null hypothesis. If the test statistic t obs was out here in the darker blue area, then on either side of the graph, that is, we would reject the null hypothesis. But in this case, we're going to retain the null hypothesis. So our statement of findings: performance on an exam is not significantly different after silent studying compared to studying with music. And we can report our t obs value of 0.81, put the degrees of freedom here in parentheses, as I mentioned before, with correlation. In this case, it's 8, and then our p-value, which is 0.44, which I didn't show that to this point, but basically you could use, again, you could use software like R to report that for you. I just wanted to close with another example just to show how sample size can influence the results of a t-test. So here we have data on basically how much money people spend on movies per month. And we're looking to see how it differs for New Yorkers, people from Kansas, people from California. And what you can notice right away is that basically people from California and people from New York seem to spend about the same amount on music. Just looking at this visually, we can look at the averages of $17.72 for California, $18.17 for New York, and we can basically see that those are similar, but for people from Kansas seem to spend considerably less on movies, $13.74 on average. So if we have data from 300 people from each of these states, and we run these t-tests, basically what we'll find is that when comparing New York with Kansas, the p-value is incredibly small. So this is a significant difference between Kansas, $13.74, and New York, $18.17. That's a significant difference. When comparing New York with California, as I mentioned before, as you might expect, there's no significant difference here. These averages are close enough that just that little difference between them is probably just due to random chance. So p is 0.16. So not less than 0.05, therefore not a significant difference between New York and California. However, if we collect data from not 300 people from each state, but rather 100,000 from each state, then basically what you would find when you conduct these t-tests is, even though like now the sample difference between California and New York is even less. And in fact, if we could just go back and look at this, here it was actually slightly higher for New York. Here it's slightly less for New York by 5 cents on average. Because these are different people, it's a lot more people, and we have maybe a little bit more precise average of what represents the population, because we've sampled so many people. But basically, when we compare New York versus California, the p-value is 0.0026, suggesting it's a significant difference. With New York versus Kansas, we still have about the same p-value as before, significant, no surprise there. But with New York versus California, it's now suggesting that this 5 cent difference is statistically significant. So the point here is just to say that sometimes statistical significance does not really align with sort of real world practical significance. In this case, it's a 5 cent difference. It's really not that big a difference, but because we've sampled so many people and we're approximating the actual numbers of the population, there's a significant difference of 5 cents. So just so you're aware that there is the possibility for researchers to basically manufacture a significant difference by collecting so much data that it's almost impossible for there not to be a significant difference. So that's just something to be aware of. So that is all for our coverage of t-tests for now. We'll look at another example in class, and I hope you have a good one. I'll see you soon.